Good day, everybody. How are you all doing? Today we are going to discuss about the standard normal curve. So I share my computer screen with you. Standard normal curve. Use the probability density curve to describe a population. Consider a data set consisting of vehicle emissions. We can visualize this data with a relative frequency histogram. So relative frequency on the vertical axis, and we have different groups or classes of data, each class with this one. Class intervals are chosen so that each rectangle represents a reasonably large number of vehicles. Okay. So we are looking at vehicle emissions. Okay. Vehicle emissions is a continuous random variable. Why it is a continuous random variable? Because it varies from 0 to 1. It can take decimal values and it is measured. So it can take any interval or any value in the interval. For the first group, it between 0 and 1. So decimal values are possible. Vehicle emission is a continuous random variable. Recall that a continuous random variable is one whose possible values can be any value in some interval. That means for if you consider the first interval between 0 and 1, it can have decimal values. Suppose that the sample of vehicles was very large, consisting of millions. Okay, because the amount of emissions is continuous variable, there would be a reasonably large number of vehicles for each rectangle, even for small class intervals. So the difference between the top diagram and the bottom diagram, in the bottom diagram, we have millions of vehicles. So we have divided the groups of data. So 0 to 1 has been divided into many groups in between 0 and 1. Why? Because we have so many vehicles, even if the class width is small, we have large number of vehicles in each interval. Okay. And we are measuring vehicle emission. I think it's in some grams per miles, something like that. So between 0 and 1, we have many classes in the bottom, second diagram in the bottom. It's a relative frequency histogram, just like one on the top. The only difference in the bottom one is that we have more number of data points in each group or each class. Such a histogram would look smooth and could be approximated by a curve. So basically, you join the roofs of each curve. The curve used to describe the distribution of this variable is called a probability density curve. The probability density curve tells us what proportion of the data falls within a given interval. Okay, so it tells us what proportion of the data, total data, falls within a given interval. So we have a relative frequency or probability on the vertical axis and groups or classes of data, in this case emission of particulate material coming out of the tailpipe of cars on the horizontal axis. And because we have so many vehicles, the group width can be made small. Okay. And why it can be made small? Because there will be still large number of data points in each group because of millions of vehicles that we are testing. The area under the probability density curve between two values A and B represent the proportion of population whose values are between A and B. It can be also interpreted as the probability that a randomly selected value from the population is between A and B. So basically, area under the probability density curve between A and B tells us what proportion of the population will fall between A and B, or what is the probability, okay, that a particular random variable will have value between A and B, okay. So in this case, you're looking at the area under the curve as 0.17 between 3 and 4. What is the interpretation of this 0.17? It is the area under the curve with vertical boundaries at 3 and 4. So two interpretation of this possible. The first one is the proportion of the population with values between 3 and 4 in this area is 0.17. So proportion of the entire population with values between 3 and 4 is the area, 0.17. You can also look at it as the probability that a randomly selected value is between 3 and 4, and that probability is 0.17. So there's a 17% chance, because 0.17 times 100 is 17% chance that the random variable is between 3 and 4. Okay. The region above a single point has no width, thus no area. Therefore, x is a continuous. Therefore, if x is a continuous random variable, probability at x equal to a is 0. Why? Because there is no width at a. So if you're trying to find the area of the rectangle at a, because it has no width, although it has a height, the area is 0. Thus, it means that probability of a less than x less than b is same as a less equal to x less equal to b for any numbers a and b. The difference between probability of a less than x less than b, here the endpoints a and b are not included, whereas in the second expression, probability of a less equal to x less equal to b, both a and b are included. These two probability values are equal because it does not matter whether you include the endpoints or not, because the probability at those endpoints, only at those endpoints, exactly at those endpoints, is 0. So whether or not you include the endpoints, it does not make any difference. For any probability density curve, the area under the curve is 1. Why? Because sum of the probabilities we have learned before is 1. Because this area represents the entire population. Consider the probability density curve with some areas indicated. Find the proportion of population between 0 and 1. That area is 0.63, so 63% of the population is between 0 and 1. The probability that a randomly selected value will be between 1 and 2, and that is 0.23. So there is a 23% chance that a randomly selected value will fall between 1 and 2. The proportion of population that is between 0 and 2. So you add up the two areas, it is 0.63 plus 0.23 is 0.86. So 86% of the population is between 0 and 2. The probability that a randomly selected value will be greater than 2. We know the total area under the probability density curve is 1, out of which between 0 and 2, it is 0.63 plus 0.23 is 0.86. So greater than 2 will be 1 minus 0.86, which is 0.14. So there's a 14% chance that a randomly selected value will be greater than 2. So what did we do? Total area under the curve is 1, always for probability density curve, out of which area from 0 to 2 is 0.86 under the curve. So area greater than 2 will be 1 minus 0.86, which is 0.14. A uniform distribution is one in which the values in any region are equally likely. The probability density of a uniform distribution is a horizontal line. Imagine when a traffic light turns red. It stays red for 30 seconds before it turns green. If you pull up to the light when it is red, the amount of time you will wait before the light turns green is uniformly distributed between 0 and 30 seconds. What does it mean? Between 0 and 30 seconds, the probability is constant. It's 1 over 30. Okay. Height is 1 over 30. And at 30, what happens? The probability drops because from red, the traffic light becomes green. Okay, so no longer it is red. So what is the total area of the probability density curve under the curve is 1 over 30 multiplied by 30 is equal to 1. So its height is 1 over 30 because the width is 30. So 30 times 1 over 30 is 1. So the area under that probability density curve of uniform probability distribution is 1, and its height is 1 over 30, its width is 30. So width times height is 1 over 30 times 30 is 1. Probabilities of uniform distribution are straightforward. The probability of an event corresponds to the area of a rectangle. Example, find the probability that the waiting time is between 5 and 15 seconds. We see the height is constant at 1 over 30 between 5 and 15. So the area of the rectangle between 5 and 15, or area under the probability density curve between 5 and 15, is the width, which is 15 minus 5, 10, times the height, 1 over 30. So 10 times 1 over 30 is 10 over 30, or 1/3. The waiting time at a bus stop for the next bus to arrive is uniformly distributed between 0 and 10 minutes. Find the probability that the waiting time is less than 3 minutes. Less than 3 minutes means up to 3 minutes. The width in this case is 3 minus 0 is 3. And what is the height? 1 over 10. Why? Because the probability density is uniformly distributed between 0 and 10. So the height has to be 1 over 10 because the width is 10. 10 times 1 over 10 is 1. So part A, the width is less than 3 minutes, width is 3, and height is 1/10, 3 over 10th, or 0.3, 30%. Okay. Find the probability waiting time is greater than 6 minutes. Now it is between 6 and 10. So the width is 10 minus 6, 4 multiplied by the height of 1/10, 4 over 10th is 0.4. Find the probability that the waiting time is between 3 and 8. Here the width at the base is 8 minus 3, 5 times 1 over 10. So 5 by 10, or 0.5. Use a normal curve to describe a normal population. This is a bell-shaped curve, relative frequency or probability on the vertical axis and groups of data on the horizontal axis. Bell-shaped curve is called a normal curve. Probability density curves comes in many varieties depending on the characteristics of the population they represent. Many important statistical procedure can be carried out using a typical probability density curve, with using only one type of probability density curve called a normal curve. It is a bell-shaped curve. It is symmetric. What is symmetric? So if you think of the place where the peak is the highest, or the relative frequency is the highest, that is the center of the curve in the base. It's symmetric because on the left of that vertical line at the center, area in the left is equal to area in the right. Normal distributions have one mode, and the distribution is symmetric around the mode. That means one value on the horizontal axis has the highest relative frequency, only one mode. Remember, mode is the number that appears maximum number of times, that is maximum relative frequency. In this case, on the horizontal axis, there's only one point whose relative frequency is highest, and that is the mode. Normal curves extend infinitely far, both to the right and to the left. Although it looks like that the tail on the right comes and touches the horizontal axis, actually it never touches the horizontal axis or goes below it. The population mean determines the location of the mean. The population standard deviation measures the spread of the population around the mean. Therefore, the normal curve is wide and flat when the population standard deviation is large, as in the dash curve on the left, and when the curve is large, and tall and narrow, as in the solid curve on the left, when the mean, so both the curves have the same mean at 0. The dash curve is more spread out because the standard deviation is 2, whereas the standard deviation of tall narrow curve is 1, so it is not so much spread out as the dash curve. The mean and median of a normal distribution are both equal to the mode. The normal distribution follows the empirical rule. What does it mean? At the center, you have the mean, which is equal to median, equal to mode. This is on the horizontal axis, where the relative frequency is highest. If you go one standard deviation on the right of the mean and one standard deviation on the left of the mean, that is, one standard deviation on the right is mu plus sigma on the horizontal axis, draw a vertical line to meet the probability density curve, and then you go one standard deviation on the left, mu minus sigma, draw a vertical line to meet the curve, the area under the curve between one standard deviation on the right and 1 standard deviation on the left is 68%. Comes from the empirical rule. Similarly, 2 standard deviation is 95% and 3 standard deviation is 99.7%. So here they basically work out the numbers, they find out the mean and the standard deviation of this distribution and show that approximately 68% of the data will fall within 1 standard deviation. 95% of the data will fall within 2 standard deviation from the mean. Okay. So we do not know all the values in the population, body temperature, empirical rules. So areas under the normal curve. The area under the normal curve represents a proportion of the population or can be interpreted as probability. It is therefore necessary to find areas under the normal curve other than those specified by the empirical rule. What is the empirical rule? 1 standard deviation 68%, 2 standard deviation 95%, and 3 standard deviation 99.7%. So the question is, how will you find area under the curve? Because area under the normal curve gives you probability between two boundaries. So sometimes they're outside the empirical rule. So we have to know how to find the area under the normal curve in different cases. So we will forget the tables. We're not going to use the tables. We will go directly to the calculator. So TI-84 plus. Okay. On the TI-84 plus calculator, the normal CDF command is used to find the areas under a normal curve. 4 numbers must be used as the input. The first entry is the lower boundary of the area. The second entry is the upper boundary of the area. The last 2 entries are the mean and the standard deviation. This command is accessed by pressing second and verse. So find the area to the left of z is equal to 1.26. Left, as you see, the highlighted area is to the left of 1.26. Remember, at the center where the peak is the highest, this is the standard normal curve, z is equal to 0 at the center where the peak is the highest. So 1.26 is on the right of 0, and anything to the left of 0 on the horizontal axis is negative z values. Here we want the area to the left of 1.26. Sometimes this is called the cumulative area up to 1.26. So also to note that this is a standard normal curve whose mean is 0 and standard deviation is 1. So we press second verse and then we scroll down to number 2, which is normal CDF. The lower boundary is a very large negative number on the left. So it will be negative because it's on the left of 0. And how do you indicate a very large negative number? In the calculator, it's already set up as -1, minus because it's on the left, on the lower boundary, 1 E. E stands for exponent 99. That means -1 followed by 99 zeros, a very large negative number, -1 followed by 99 zeros. Instead of writing 99 zeros, we use the if exponent. So the lower boundary, if we start our calculation from the extreme left, is -1 E99. The upper boundary, we only want to go up to 1.26, so type 1.26. The calculator is set for the standard normal curve. Mean is 0, standard deviation is 1. Paste, enter, and enter. And the area is 0.896, much like what's in the screen. Area to the right of, now -0.58 is on the left of 0. We want the area to the right of -0.58. In this calculator, TI-84, we always start our calculation from the lower boundary. In this case, it's -0.58. So we again press the second verse, go to number 2, scroll down, hit enter. Lower boundary is no longer -1 E99. It's minus next to the enter on the left of enter, lower boundary, -0.58. The upper boundary is a very large number on the right, so it will be positive. So we will type 1, then second comma will give me the E exponent and 99. So what did I do? 1 followed by 99 zeros is the upper boundary. The mean and standard deviation, mean remains 0, standard deviation is 1, paste, enter, and enter. And the answer is 0.719. Now we are between boundaries minus 1.45, which is on the left, and 0.42, which is on the right of 0. Okay. So again, second verse, number 2, lower boundary, we always start from the lower boundary is minus 1.45. Upper boundary is 0.02, 0.42, sorry. Mean is 0, standard deviation is 1, paste, enter, and enter. Enter twice. And the answer is 0.5892. Okay. We don't worry about this. Find z-scores corresponding to areas under the normal curve. Again, we will go directly to the calculator. So we have been given area to the left of a z-score. Okay, area is given in this case, area will be given to the left of a particular z-score. We have to find the z-score. So here is a problem. We have been finding areas under the normal curve from given z-scores. Many problems require us to go in the reverse direction. That is, we are given the area to the left of z, we need to find the z-score. Such as in this case, area is 0.26. We are not going to use second verse 2. Instead, we will use second verse 3. This area, the first line on second verse 3 is area. Area is always the area on the left of unknown z. Z is question mark, that's the unknown z. So this area we can type 0.26, leave the mean at 0, standard deviation is 1. For standard normal distribution, go down to PEST. Whenever you are on PEST, you have to hit enter twice. And the answer is minus 0.643. Okay. Just like this. Okay, find the z-score that has an area 0.68 to its right. Here the area on the right is 0.68. Calculator only takes area to the left. We know the total area under the curve is 1. Area to the right of the unknown z is 0.68. So area to the left of the unknown z is 1 minus 0.68, which is 0.32. So second verse, number 3, area is 0.32. Mean and standard deviation do not change. Paste, enter and enter. And the answer is minus 0.4676. Find the z-scores that bound the middle 95%. Middle 95% means the central highlighted area is 0.95. Now we know the total area under the curve is 1. So area in the two tails is 1 minus the area in the center, which is 0.95. 1 minus 0.95 is 0.05, but that is the area of two tails. Because this normal curve is symmetric, area in the two tails is 0.05. Area in each tail will be half of that, which is 0.025. So area in the left tail is 0.025, area in the right tail is 0.025. Again, to repeat what I did, to find the area in the two tails, I subtracted from 1 the central area, which is 0.95. 1 minus 0.95 is 0.05. That's the area in the two tails. Normal curve is symmetric, standard normal curve. So area in each tail are equal. So take that 0.05, which is area in the two tails, divide by 2 to get the area in each tail is 0.025. So now I do second verse 3. Area in the left tail is 0.025. And I want to find that unknown z1. And I paste. Enter and enter. And that value is minus 1.9599, sometimes simplified to minus 1.96. How to find Z2? Well, think of the area in the center is 0.95. Area in the left tail is 0.025. So area to the left of the Z2, the boundary on the right, is 0.95 plus 0.025, which is 0.975. So second verse 3 again. Now instead of only 0.025, it will be 0.025 plus 0.95, which is 0.975. So area type 0.975, Leave the mean and standard deviation alone, go to down to paste, enter and enter. And that value is positive 1.9599. Okay, forget the Excel. Find the z-scores that bound the middle 90%. So area in the two tails is 1 minus 0.9, which is 0.1. Divide that into two equal parts. So 0.1 divided by 2 is 0.05. So area in the left tail is 0.05. To find z1, go to second, verse 3. Area is 0.05, comes from 0.1 divided by 2. Mu is 0, sigma is 1, paste, enter and enter. And that value is minus 1.645. How do I find Z2? 0.9 plus 0.05 is 0.95. Area to the left of Z2. 0.9 in the center plus 0.05 in the left tail. 0.9 plus 0.05 is 0.95. So second verse 3, I type 0.95 as the area and go down to paste, and I will find it is positive 1.645. One thing you notice, the difference between Z1 and Z2. Z1 is on the left of 0, so its value is minus 1.645. Z2 is located the same distance away from the center, which is at 0, but it's on the right of 0, so its value is the same value as Z1, but it is positive 1.645. Okay, so we are done here. I'll stop here. If you have any question or comment, write me a note. If you like this video, please give me a thumbs up. I really appreciate that. If you like this video, share with your friends. And please subscribe to my channel by hitting the red subscribe button and also hit on the bell. That way you will be notified every time I upload a new video. Okay. Thanks for watching, and please do not forget to watch me tomorrow when I'll present another interesting situation or problem. Thank you. Thanks for taking time to watch this video. See you. Take care. Have a nice day.